Hello, everybody. I'm going to talk about phenotypic responses of trees to climate change, focusing on the results got from the free air humidity manipulation experiment. First, briefly, some words about the background. There is a general prediction that climate change trends will enhance growth of trees and productivity of forest ecosystems due to climate warming and earlier start of the growing season in spring. So climate warming has double effect. First, it leads to longer growing period. Here, as you can see, the earlier the bud break in spring and longer the growing period in autumn, the higher the productivity. The second effect is related to enhanced nutrient uptake and carbon sequestration. Here I present data of the experiment performed in Sweden. Soil temperature elevated by 5 degrees will substantially increase stem volume increment in novice growth. Here, data from one meta-analysis. This analysis revealed that changes in stem diameter and non-leaf biomass are more closely related to changes in night temperatures than in day temperatures. And the last graph indicates that biomass mostly increases in boreal and temperate species in response to temperature rise and declines in tropical species. And one more important result from the same study, rising temperature declines the Roottoshoot ratio, so there will be enhanced biomass allocation to above ground organs. Climate change scenarios predict increase both in air temperature and precipitation in northern Europe. As Ulo mentioned already, wetter regions will become wetter and drier regions drier. So northern Europe belongs to the zone of 10 to 20% increase by the end of the century. The same climate models based on detailed input data predict for Estonia precipitation increase up to 20% by the end of the century. And one more important aspect of climate change at high latitudes is depicted here. Frequency of rainfall will decrease in nighttime and will increase substantially in daytime. What does it cause? It will cause bigger increase or significant increase in mean air humidity, as daily rainfalls have much bigger effect on mean air humidity. What about real trends in climates? In fact, increase in mean annual precipitation is well correlated with increase in precipitation frequency. In left graph, data for Northern Europe are indicated. And the right graph indicates that both relative humidity and specific humidity of air has increased in Northern Europe during the last decades. In order to study the effects of increasing atmospheric humidity on tree structure and functioning. The free humidity manipulation experiment was established in Estonia. There are two experimental species, silver birch and hybrid aspen. And here you can see two views on our experimental area. During the 10 last years, we have performed extensive field and also lab studies on this topic. These studies indicated a number of structural and functional responses in one or both experimental species. Most of the phenotypic responses are mentioned in this graph. The arrows indicate the direction of the effect of increasing humidity, increase or decrease. Because of limited time, I can comment only some of them. Let's start with structural responses. We observed retardation of foliage development at different levels of organization. So at the individual leaf level, whole tree and the sand foliage levels, and the consequences of this effect are not hard to comprehend because biomass production of trees is directly proportional to their foliar area. Next, larger investments in xylem in relation to foliar area increase the ratio of non-photosynthetic to photosynthetic tissues, and this brings about larger maintenance respiration costs, so less resources remain for growth. Next, reduced atmospheric evaporative demand weakens environmental pressure for development of efficient water conducting system, inducing changes in tissue proportions of tree stems. Increasing proportion of living parenchyma tissue brings about larger maintenance respiration costs. Next, diminished nutrient uptake caused by reduced transpiration flux induced changes in root morphology, mimicking responses to soil nutrient efficiency. Also, there was not nutrient efficiency because this plantation has been established on previous agricultural land. So we observed increase in specific root area and specific root length and decrease in root tissue density, quite typical responses to nutrient deficiency. Next, reduced density of glandular trichomes at leaf surface leads smaller content of tree terpenoid and flavonoid glycans, and this makes plants more susceptible to herbivores. Also, there were changes in chemical composition of epicuticular waxes, and this reduces hydrophobicity of cuticle and increases water retention of leaf surface, and this brings about higher risk for fungal pathogen attacks. It's not merely a hypothetical consideration, as the frequency of fungal damage is caused by Cryptosporella petula is much higher in humidified plots of the farm site. Let's continue with functional responses. Diminished transpiration flux resulted in reduced nutrient uptake in silver birch, and this caused decline in photosynthetic capacity. Foliar phosphorus concentration decreased more than nitrogen concentration, and as a result, phosphorus-nitrogen ratio fell below optimum level for silver birch. Several works have proved that phosphorus-nitrogen ratio is more important than concentrations of other nutrients in leaves in determining limitations to photosynthesis. Furthermore, we established a fine correlation between foliar phosphorus concentration, phosphorus-nitrogen ratio, and maximum electron transport rate. In this table, changes in photosynthetic parameters have been shown. Next, metabolomics analysis of silver birch revealed significant changes in several metabolic pathways, and here I want to mention three of them. First, changes in nitrogen metabolism, changes in in contents of amino acids in particular. Second, changes in shikimate pathway. And third, changes in biosynthesis of secondary metabolites, flavonoids. As a result of humidification, contents of alanine, valine, and glutamine decreased in leaves, while contents of glutamate and aspartate increased. But decline in shikimic acid content may disturb biosynthesis of aromatic amino acids. But anyway, these 2 points together most likely disturb normal protein synthesis, and this has consequences on both photosynthesis and growth. But increase in secondary metabolite contents like quercetin and catechin, it's a firm evidence of the stress response. Tens of papers have shown that flavonoid biosynthesis is upregulated in response to different stress factors: osmotic stress, oxidative stress, cold stress, drought stress, and also in response to hypoxia, like in the present case. We observed differential effects of air humidification on hydraulic versus gas exchange conductance. And due to reduced hydraulic conductance in Irbid aspen saplings, canopy conductance to water vapor decreases more rapidly in response to falling water potential, as shown by this line. And this will impose constraints to gas exchange. Also, we observed disproportionate changes in sensitivity of stomatal versus leaf hydraulic conductance to water deficit in silver birches. And this will bring greater risk of desiccation-induced hydraulic dysfunction in case of weather extremes. Both gas phase conductance and liquid phase conductance fell more steeply in humidified trees, but the decrease and decline was much steeper in hydraulic conductance. Of course, different effects are combined in nature, and the mechanisms are interrelated. And here I show you how effects of nutrient uptake, hydraulic and allocation effects are combined, and all together have an effect on plant performance, on plant growth rate. Our studies revealed that in addition to quite direct effect of increasing atmospheric humidity, its effect is also mediated by changes in soil water content, causing hypoxia. And these different effects together resulted in growth retardation. What we observed in both species in this table, data on growth data on silver birch are given, and in this graph, data on hybrid aspen. And one of the most recent results, increasing air humidity affects trees' growth depending on their social or competitive status. Competitively advantaged trees were most strongly affected, and disadvantaged trees were never affected by this treatment. What we can conclude from this story, first, impact of increasing air humidity on trees functioning is very complex, and their phenotypic responses are highly diverse. And second, expected climate change induced growth stimulation of trees at northern latitudes could be smaller or null if temperature rise is accompanied by a rise in atmospheric humidity. And at last, I want to thank my colleagues from the plant ecophysiology group and also our collaborators from the University of Eastern Finland. Thank you.